Before we move on, let us get some terminology down that is going to be with us for most of this class. We've already touched on a bunch of these things, but let's get this all down clearly. It's definitely worth that investment. First of all, a training example is one of the examples that we're going to learn from. It's a pair of example and its class. Okay? Sometimes called a training instance. Statisticians like to call it a sample. A set of training examples is often called a training set. So there's different names for this. The target function is the true function that you're trying to learn. If the function is Boolean, we often call it a concept. Like, for example, I'm trying to learn the concept of chair, right? And then I have examples of chairs and say examples of other pieces of furniture, right? In that case, the function is a concept. The hypothesis is a candidate function. So the function is only accessible to the gods. We don't know it. We just have examples. What we're going to be generating is hypothesis. Of course, our goal is to generate a hypothesis that is as close to the function, to the true function, as possible. If the hypothesis is Boolean, as I just said, we call it a concept. The examples for which the hypothesis is value true are called the positive examples. So, if I'm trying to learn the concept of a chair, a picture of a chair is a positive example. A picture of a table, on the other hand, is a negative example. Okay, so this terminology, obviously, we're going to be using this a lot in little examples. We're going to have positive and negative examples of a concept. And we're going to see, well, how do we learn to divide them? The function that we learn, if we're in a discrete problem, which we're going to be, as I said, looking at most of the time, is called a classifier, right? So classifier is actually what the learner outputs. Remember, a learning program is a program whose output is a program, right? Is a method program in some sense. And that program is called a classifier, right? A classifier is something that takes an input and produces a class, okay? People often abuse language by calling the learner a classifier. So you have to be a little bit careful when you hear classifier. Sometimes what people really mean is the learner that learns the classifier. Strictly speaking, the classifier is the function that comes out. Once you have the classifier, you can throw away the learning algorithm and you can just have that thing that you post on the machine that tells people what to do. That's the classifier. Okay? The values that the classifier outputs are called the classes. For example, I might be trying to classify text into topics, in which case the topics are the classes. Often they're also called labels or class labels, right? My goal is to label my objects with, this is a chair, this is a table, this is a dog, this is, etc., etc. Okay? The hypothesis space is the set of all hypotheses that can be output by our algorithm, right? If something is not in the hypothesis space, then your algorithm can't output it, no matter what it does. If what you have is a decision tree learner, it can only output a decision tree. It cannot output a neural network. Okay? The version space is actually a more subtle but very interesting notion. The version space is a subset of the hypothesis space. It's the subset of the hypothesis. It's the subset of hypotheses that are consistent with the data that I've seen. Right? So the picture, like we did in our little, M of n example. I start out with all my hypotheses, right? Before I've seen my example, it could be any M of n rule. But then as I look at each example, right, some of those hypotheses get thrown out. They don't agree with the example, so they can't be the right one. The version space is the hypotheses that remain after I've seen the examples. Okay? And when I see more examples, when I increase the size of my training set, the version space can only shrink, right? Once something is out, it's out forever. On a bad day, right, what happens is that my version space shrinks to 0. Right, like it did in the case of the if-then rules. And what do you know in that case, when your version space shrinks to 0? Yeah, your hypothesis space was wrong and you need to try another one. Okay? Another thing that can happen is that, more than one remains, right? In our case, there was only one good M of n concept, but there might have been a bunch, right? In which case, you have a number of options. You can return all of them. You can pick one of them at random, or probably the best one is you average them. You take all of those and you just predict, you let them vote and the majority wins. Yep.
Could you explain the classifier once more?
Classifier, for example, a spam filter is a classifier, right? It's a program that takes in an email and outputs spam or not spam. A learner, right, is naive Bayes. It's the system that produces the classifier. So a learner has as input a bunch of emails and yes, spam, no spam, and outputs a classifier. Classifier is what you then apply to new inputs, right? Classifier is what, at the end of the day, say replaces the human, right? Replaces the credit evaluator to make the decision, or replaces the doctor, or helps the doctor to diagnose.
I mean, so is the classifier and the machine learning system really truly distinct? I mean, aren't there cases where, I don't know, where you get your spam and you say, well, I guess that was spam, and you don't do anything to...
They are different. The one case where the boundary becomes fuzzy is in instance-based learning, because then your learning just consists of remembering the instances. But even then you can make and should make a distinction between the classifier and the learner, right? The classifier is taking our new instance and finding the closest instance and outputting its value, right? The learner, in that sense, in a way, is actually not doing anything. But there, the distinction between a learner and a classifier is the same as the distinction between a program and its output, right? A program and its output are not the same. In machine learning, the program is the learner and the output is the classifier. The reason it's easy to get the two confused is that, first of all, people abuse language and call learners classifier. The other one is that it's easy to forget that learning is a program that produces a program. And then you confuse those two programs, but they are different. Remember, for the program, you're only in a space that's exponential. Right? The space, right? But the learner is solving a problem that's in the doubly exponential space. So it's a much harder problem. More questions? Okay. So, again, before we start looking at specific representations, algorithms, and so on, let's look at what some of the key issues are that we're going to be thinking about as we look at all of these different technologies, right? And they are very much the same issues that recur. Some things are technology specific, but many of them are common to all of them. It's very important to understand what they are, because no matter what algorithm you're using, they will arise. And also, this is the kind of knowledge that will still be applicable even if tomorrow you're using an algorithm that you've never seen before. So the first and very obvious one is, what are good hypothesis spaces, right? This is the first decision that you have to make. How do you pick a hypothesis space? How should you do that? Well, one thing to do is to learn from the past, right? What hypothesis spaces have people used in the past that worked for them, right? Why do we use decision trees today? Because they've worked very well for a lot of problems in the past, so with any luck, they might work for your problem as well. Okay? Are there general principles that we can come up with in designing and choosing hypothesis space? There are some, and we'll look at some of them. At the end of the day, however, there's a lot of, black magic, art, heuristics, intuition, whatever you want to call it, right? It's not a science. There's an art side to this. The second question, of course, is, well, given these spaces, right, let's take, say, decision trees, right, very widely used. Now, if that is the hypothesis space that I'm going to use, now what algorithms work well with that space? And it's not the case that one algorithm works well with all spaces. For different spaces, you will have to pick different algorithms. And we would also like to come up with not just specific algorithms, but also general design principles for matching algorithms to spaces. The next question, in some ways, is the quintessential question of machine learning, is like, what can I do to optimize my accuracy on the points that I haven't seen? Machine learning is very different from really any other field that I know in this respect, in the sense that lots of things are optimization, right? Like operations research is optimization. People solve all things by optimization, right? Search algorithms in computer science and AI are optimization. But in all of those cases, I actually know what I'm optimizing. The problem is that there's a large space to search, and searching it efficiently is difficult, but I know that if I was able to perfectly optimize that function, I would have my answer by definition. In machine learning, it's different. My objective function is only an approximation to what I want. For example, accuracy on my training data is not what I really want. What I really want is accuracy on the data that I haven't seen. So in machine learning, I'm actually optimizing a function that I don't know. And that's what makes it tricky. What I'm going to have to do, of course, is optimize some other function that's a surrogate for the function that I know. And now the question becomes how I do that. And there's a very lot of, deep and interesting ideas that go into doing that. There's also, some very simple heuristics that we can use to do that, and of course, we will see some of both of these. The next question is what you might call the statistical question. And this is what, statisticians, or at least academic statisticians, worry about for a living. And, practical statisticians and practical machine learning people also need to worry about this if they want to be believed, is, okay, you've just produced a great, spam filter. You say it's great. How can I be sure that it's great? If you tell me that it's great because it fits all the training data perfectly, I'm going to be very suspicious. In fact, if you're ever in the position of hiring somebody else to give you a classifier, right? If you're the boss instead of or the client, the first thing that you should do is take some of the data and keep it to yourself. Right? Let's say you're hiring somebody to design, a spam classifier for you. Don't give them all the examples of spam and not spam. Keep some to yourself. And then if what they do is like they've overfit the data that you gave them, when you try it on your data, you'll see that it's a failure. So what happens is that when they're doing their learning, they have to worry about how well their learning is going to be doing on the data that you have and they haven't seen. Okay? Another question for them, and also the question for you once finally I run it on the whole data, and now I'm going to deploy in the real world, is like, how can I be confident that this thing is still going to be accurate on future data, right? Can I have measures of that uncertainty, and can I, minimize that uncertainty, right? There's a lot of good stuff from statistics that we can apply here, okay? So this is the statistical question. The next question is what you might call the computational question, right? And this is the usual question. Well, sure. Let's say you have a very good method for learning things, and you can be very confident of the results. If it takes exponential time in the size of the data, well, we can't do it. And unfortunately, we're going to run into things that the naive approach would take exponential time in the size of the data almost all the time. There are some algorithms like, say, naive-based that don't, and that's a large reason, part of the reason why they're used a lot. But for a lot of the more interesting algorithms, the NP hardness of it really comes to bite. Okay? So now the question becomes, how can we design an algorithm that maybe sacrifices some guarantees for actually returning something in practice? Okay? So this is the computational question. It's not enough to have something that is statistically sound. It also has to scale. On the other hand, it's also very important to have, it's not enough to have something that scales. I unfortunately see people out there in the real world doing a lot of stuff with Hadoop and big data clusters, and we can mine this data, that, and the other, and return a pile of junk. Right? So there's no point in having something that scales if what it does is return you a pile of junk. Right? So you really have to worry about both the statistical and the computational question. Moreover, and finally, you have to worry about what you might call the engineering question. The engineering question is the following. We've just defined this problem, inductive learning. I want to learn a classifier from printing examples. Most of the time, the problem that you have to solve in the real world does not come cleanly expressed in those terms. You have to figure out a way to turn it into such a thing. Right, these days, everybody uses classifiers for spam filtering, but it was actually an idea in somebody's mind one day, in particular some guys at Microsoft Research, that, hey, we can turn the problem of spam filtering into a classification problem and apply machine learning techniques. So this process of figuring out how to turn your problem into, a classification problem, right, into a supervised learning problem, could actually be a very subtle one that requires a lot of insight and creativity on your part. In some cases, it's very straightforward. In most cases, what happens is that once somebody figures out that you could do, well then, so like the whole industry develops around it. But this can itself be a very hard problem, and obviously it's important because if you can't do that part, then you can't do anything. Also, often what can happen is that you do that part, but in doing it, you kind of shoehorn it into the problem into a form that kind of neglects a lot of the important aspects, and then you'll fail because of that. In fact, this is what happens a lot with spam filters. You shoehorn your problem with spam filtering into building a naive-based classifier, and then guess what the spammers do? They immediately set about exploiting the assumptions that your naive-based classifier made and making sure that they can defeat it that way. Okay? So this part is also very, very important. Questions? Yeah.
So how about unlearning as you proceed? Where does that come? Like what if you have learned something but that's no longer true?
Yeah. So exactly. So that, we're actually going to touch on that in just a little bit. So there's two types of learning that you can do. To jump ahead a little bit, there's what's called batch learning, where you assume that you're given all your data, all the data you're ever going to see, and you learn on that. And then there's online learning, where your learner is always deployed, and you're changing the learner as the data changes. In the early days of data mining, people did mostly batch learning, right? You would do a data mining project like you would come to me with data, I would spend 6 months on it, and then I would give you a classifier. These days, more and more, right, what you have is online algorithms. If you look at companies like Google and Amazon and Facebook and whatnot, they have online algorithms. They're always learning. Every time that you go to Amazon and do something, it updates your model. It's more challenging, but at the end of the day, it's what you want to do most of the time. We're going to focus mostly on batch learning because it's simpler and easier, but usually for every online algorithm, for every algorithm, there's a batch version or multiple versions, and there's an online version or multiple versions. Good question. More questions?
Question about terminology. So a hypothesis would be something like M of n example that you presented.
Yeah.
An hypothesis space is a set of hypotheses that you allow, right?
Right, so a hypothesis space is the set of M of n concepts.
Okay.
A particular M of n concept is something like 2 out of x1, x2, and x3. If then rules is a hypothesis space. The rule, if this email contains the word Viagra and 3 exclamation marks, it's spam. That is a particular hypothesis. Okay? So we choose a set of hypotheses, and then the learner produces one specific hypothesis or a small number.
Generally, it's mapped to one representation. You decide that the hypothesis space is mapped to a decision tree, for example.
Yeah. Exactly. So a typical machine learning algorithm, right? You pick the hypothesis space and say, well, now I'm going to use decision trees, so let's use a learner for decision trees. These days, in the early days, you would have like these single algorithm systems. This is what any good system has from many of these, companies like IBM and Oracle, Microsoft. Is like you have a whole suite of these algorithms, and you could even have a meta-level procedure to try to figure out, well, should this be a decision tree or should it be a neural network? Should it be a decision tree with neural networks hanging from the leaves? That tends to get very expensive and to risk a lot of overfitting, but it's possible as well. More questions? Okay. So a few more things. So, So as we look at our hypothesis spaces, and we're going to go through a bunch of them in this class, here's a few dimensions that we want to consider because they're important. Many things are different depending on those dimensions. The first one, we've already talked about it a bunch, is the size. Does this hypothesis have a fixed size like naive Bayes, or does it have a variable size like decision tree learning, like decision trees? Right? Learning things in these two cases is going to be quite different. Another very important one is randomness. Is my hypothesis space deterministic or stochastic? Deterministic is, I tell you that this is a spam. Stochastic is, well, maybe this is a spam with probability 0.75. Again, these will imply very different things. And then there's the question of whether your parameters are discrete or continuous. Am I just making discrete choices like in a decision tree, what should be in my nodes and whatnot, or do I have continuous parameters to adjust? Okay? As in a neural network, I'm basically adjusting the weights on the neurons, and there's a large number of real numbers that I need to optimize. Or do I have a combination of both? In many algorithms, I actually have a combination of both. For example, in graphical models, what I have is I have a graph, which is a discrete structure that says what the dependencies are, but then I need actual tables of parameters specifying exactly what's the probability of what when. Okay, and finally, as we look at our algorithms, there's a number of one of these dimensions is what we're just talking about. So beyond the hypothesis space, there's a number of key dimensions along which algorithms differ. And again, we're not going to explore this space comprehensively because it would take too long. But it's good to be aware of what it is. And also, when you come upon a new learning algorithm, one of the first mental exercises that you should do is see where it fits in these dimensions. And once you know that, you already actually know a lot of things about what it's going to be. So the first one is the search procedure. The simplest kind of search procedure you could have is just direct computation. So for example, something like naive Bayes, you don't need to do search. You just compute these parameters in closed form. If you want to run things on very, very large data sets, naive Bayes is great. You just need to run through the data once, updating your parameters, and you're done. I'm told that in the early days at Google, naive Bayes was very widely used. And a lot of trying to do is like, well, it's very scalable. There's no search to do. These days, I don't know. I suspect that's not the case anymore. But nevertheless, direct computation is great when you can have it. The price of that is that probably your learner is going to have to be very limited. If direct computation doesn't do the job, then the next thing, one of the things that you can try is local search. Local search is what happens when you start with a complete hypothesis and then you modify it. So for example, when learning a neural network, you usually start with a complete neural network. It's like your brain at birth, right? Your brain's already there. The problem now is that you need to vary the weights. So you take little steps in weight space and hopefully you have something that fits the data very well, right? The other, or one other approach is what's called constructive search. This is where you start out with one small piece, not a complete solution, but then you assemble the solution piece by piece. This, for example, is what you typically do when you're learning decision trees. You start out with a small decision tree with just one node, and then you attach one more node, and then you attach another node to that node, and you do this until hopefully you have a good model. Okay? Timing. We've touched briefly on this, but it's another important dimension. You could be eager or lazy. Right? These are very expressive terms. Eager means, eager is like the good student. You don't leave for tomorrow what you could do today. You go home, you study the whole book. The following day, you already know all the material. Right? This is eager learning. is where you do a lot of work at learning time. And then, at test time, when the exam comes, you've wasted all, you can do it with your eyes closed, right? A lot of learning algorithms, probably most learning algorithms are eager. But there's also the lazy option, which your mother told you was a bad one, but actually procrastination can be a great strategy. The lazy strategy is like, nah, I'm not going to do anything today. I'm going to relax. I'm going to drink beer and watch TV. And, when the test comes, I'll just scramble. I'll improvise. Some people are good at that. Right? And unlike in human affairs, actually, in machine learning, often the lazy version of an algorithm is more powerful than the eager one. The reason it's more powerful is that when you're doing eager learning, you're doing it ahead of time. You don't know what you're going to be applying it to yet, so it has to be good for all things. Very hard. Lazy learning is like, oh, now I have this patient to diagnosis, and I just, I didn't really pay attention in med school. Like that Spielberg movie, right, about the guy who faked he was a doctor. And he turned out to actually be a really good doctor, right? So he didn't need to go to Harvard, right? He faked that he'd gone to Harvard. But then, when faced with the patient, then you figure out what does this guy have? What do I do, right? Right? For humans, this doesn't sound like a good strategy, but for machine learning algorithms, it can actually be good because now I just have to, I apply all my power to these particular cases, and I don't have to be very good in general. Okay? So lazy versus eager learning. Some representations natural in themselves to one or the other, like instance-based learning is the quintessential lazy algorithm, right? I just remember the examples, and when a new one comes along, I find similar ones. But there's really lazy and eager versions of any algorithm that you might want to think of. Like there's lazy versions of decision tree learning, for example. And a final dimension, which you already touched on, is online versus batch. In online learning, you only see one example at a time. Like predicting the stock market is a quintessential online learning problem, right? I predict whether the stock is going to go up or down, and the next day or the next minute it goes up or down. And then I incorporate it into my learning. And I keep learning as I see more things. Batch learning is, I've got a supercomputer, I've got a big data center, I'm going to throw a ton of cycles at this thing, and then I give you a product. For some things, it's appropriate. For example, if your domain is not changing a lot, and you only need so much data, batch learning is appropriate. Most of the time, however, at the end of the day, you want to do online learning. There's also a spectrum, right? You could do mini batches where you learn, like maybe every day, right? This is common, right? Every day you rerun your learning, not like with every new example. So there's variations of this, but it's important to be aware of both. Mostly we look at batch learning, but it's important to realize that there's also online versions. And as I said, in a lot of domains these days, particularly on things to do with the web and whatnot, online is more and more what people do. Okay? Questions?
Where is batch useful, like practical? I see that most of them are online.
Well, actually, there's many cases where batch is used. For example, let's say drug design, right? You give me a big batch of molecules and how they dock, right? And if I found one that inhibits the virus, I've won. I have a cure for the disease, right? So whenever the problem is not changing, right? And you only need so much data, then there's no advantage in doing it online. Batch is more expensive, but you can do more things, right? The power of batch is that I can use the examples in random order. In online, I'm forced to do I can't use the examples that I haven't seen yet. So, each one has its advantages and disadvantages. If you look at all the applications of machine learning in the world, I would say that it's still the case that the great majority of them are batch. In the domain of things like the web and whatnot, more and more online is the case. And I think in the future what's going to happen is that every organization is going to be doing, online learning. Because that's how you beat the competition, right, is you react faster than them. But even in science, it's very interesting that, if you look at things like, large sky surveys, right, that are spewing data at you every second. Or, things like, particle physics, right, particle accelerators, they're spewing like, gigabytes of data at you every second, right? In these cases, online learning might also make sense. Because basically what you want to do is you want to figure out very quickly how much of this information you want to ignore. And then you just learn from the rest. More questions?
So what is the need for the lazy version of the...
The reason for the lazy version is, there's two reasons at least. One is that eager does more work at training time, lazy does more work at test time. So if you're in an application domain where you have a lot of time at test time, but not a lot of work at training time, then you're better off using lazy. But the other reason is, the bigger reason I would say, is this thing that lazy learning is actually more powerful. a lazy decision tree learner is more powerful than an eager decision tree learner. Here's a different example that may be easier to see. Let's say you're doing linear regression, right? The statistician's basic tool, right? You have a bunch of data points, right? And now you want to fit a line through them. If you do this lazy, right, what it means is that you have to find a straight line that goes through all your data. Well, on a good day, your phenomenon is mostly linear, but most of the time your data is, it's going to be a curve. So your linear regression is not going to give good results. If you do it lazy, however, the following amazing thing happens. I have my query point now. How much money is this person going to spend? And then all I do is I take a neighborhood of that person and I fit a linear model to that neighborhood. And so in each neighborhood I can have a different model. So my overall model could be extremely nonlinear, meaning vastly more powerful than a linear regression. So lazy learning could be a really smart thing to do. It's not a good idea when you need, reactions, every second. Like if you're doing high frequency trading, forget about lazy learning. If you're learning how to control a robot, for example, lazy learning is not a good idea either. Because, that robot needs to decide what to do every 10th of a second. In many ways, actually, lazy learning is actually a very good thing for robots, but, because of the type of model and whatnot. But then what you have to do is maybe try to take your lazy model and find some way ahead of time of making it work faster. And, for each of these, approaches, there's ways to try and ameliorate its disadvantages, but, they're there nevertheless. More questions? All right, very good. So to recap, you're going to get your first project next week. The biggest part of it is going to be to implement a decision tree learner and apply it to clickstream mining. We'll also test some of the stuff that we're going to do the week after that, which is rule induction. Hopefully today you got the big picture of machine learning, why it's important and people are excited about, what it consists of, what main types of machine learning there are, and then in particular for supervised learning, what makes the problem hard and how we can go about solving it, and what the main dimensions are. Okay? See you next week, and do keep in touch by email and using the forum and so forth.